Alright, so welcome everyone to Lecture 8. We'll be talking this week about the Buchberger algorithm, and then Ken's going to continue with Chapter 3, so hopefully I only take up about half an hour or so. So let me remind you where we got to last time. So last time we proved the Buchberger criterion, which tells us how to recognize when we've got a Grosvenor basis. So remember that a Grosvenor basis G is a Grosvenor basis G being some finite set of polynomials. It's a Grosvenor basis for I if LTG equals LTI, where today if G is the set F1 through Fs, this is going to mean the ideal generated by the leading terms of the elements. Okay, so that's the condition to be a Grosvenor basis, and Grosvenor's criterion, which is the hard part of the Buchberger algorithm, which we proved last time. It says that G is a Grosvenor basis. So it gives us an effective algorithm for actually checking this equality here, which otherwise is a bit mysterious from the point of view of sort of a computational approach. So G is a Grosvenor basis if and only if when you compute the S polynomial of P and Q being elements of G, and you take the remainder upon division by G, you get 0. So we proved that last time, and maybe the high-level takeaway from that proof, the role of the S polynomials was to be something like an explicit way in which the leading terms might cancel, right? So if you think about the division algorithm, you're removing terms from a given polynomial by subtracting multiples of some fixed polynomials, the GIs, say, if you're dividing by G. So you're creating cancellations of leading terms by multiplying two polynomials by some coefficients. So in the division algorithm, you multiply f by 1, and you subtract something times G, G being one of the elements of capital G. So you create a cancellation that way. And the S polynomials are kind of like the prototypical cancellations, right? And we saw that in some sense all cancellations can be expressed in terms of these prototypical ones. And that is a formal expression in terms of the module of syzygies being free on the S polynomials. That's in CLO. We won't cover it, but what I'm expressing is an intuition that can be made a lot more formal. Okay, so that's the kind of meaning of S polynomials. They're the prototypical cancellations of leading terms. And Grosvenor's criterion says that somehow if all those prototypical cancellations can already be expressed in terms of the elements of G, that is, that's what this says, right? It says the remainder upon division by G is 0, which is one way of saying that the S polynomials can be written as a linear combination of the things in G. It's kind of a completeness condition, right? Like you've already got all the consequences of G in G. So that's a reminder. Now let me state the main theorem for my part of today's lecture, which is Buchberger's algorithm.
Nice.
What's nice?
Your pronunciation.
Yeah, I have Eleanor sitting on my shoulder. I'm scared. I know she's going to be listening to this at some point. Let this be an ideal in the polynomial ring. There's a fixed monomial order, right? There's a monomial order around everywhere because otherwise this doesn't make any sense, yeah? then a Grosvenor basis for I can be constructed in a finite number of steps by the following algorithm. That's the algorithm. Okay, it's on the next board, the real algorithm. So the input is going to be some generating set for our ideal as a sequence. It sort of matters that it's a sequence because remember we need to do some divisions. We're going to compute S polynomials and their remainder upon division, and the order of the division may matter, right? Because we don't have a Grosvenor basis to start with. So we input a generating set. The Grosvenor basis we get at the end may depend on the order, because Grosvenor bases aren't unique. That might seem irritating. I'll address that at the end when I talk about reduced Grosvenor bases, which are in fact unique. So we're going to output a Grosvenor basis which contains f, actually is an initial segment. So the beginning of the sequence G is f. And here's the algorithm. Okay, we start by setting G to be f, and then we're going to repeat the following loop until G prime is equal to G. You'll see what G prime is in a moment, and then we'll return G. So we're going to make a kind of temporary copy of G, which is going to sort of be we want to keep a copy of G as it was at the beginning of this pass through the loop, and that's called G prime. Then we're going to look through all pairs in G prime. So for each pair, I don't need to write it like that. PQ, well, yeah, okay, I guess there's a subtlety here. So for each unordered pair, PQ in G prime, we're going to compute the S polynomial. Quick question, what's the relationship between this S polynomial and this S polynomial?
-1.
Yeah, that's right.
Multiply.
Okay, so I don't have to consider both pairs, right? Hence why this is a set. So this is an implicit way of saying look through all pairs in G prime, but you don't have to take PQ and QP. So what we do is we compute the remainder. We're going to change G, right? So let's do it with respect to the original value of G at the beginning of this pass through the loop. We compute the remainder. If it's non-zero, then we add it to G. Okay, so that's it. So in this, at the beginning of the loop, we've got our polynomials in G prime. We look through all pairs, we divide them by that fixed G prime, we add the remainders to G. G's getting bigger, so it starts with G prime, and then it's G prime and the first remainder, and then it's G prime and two remainders, and so on, until we've looked through all pairs, and then we hit the end of the loop and we go back to the beginning. And we keep doing that until we didn't add anything to G, right? So this this exit condition, which it isn't clear will ever be reached. That's something I have to prove. But that exit condition means that the remainders must all have been 0. Right? So I hope, it's, of course this is based off the criterion, right? So the only part where we have to really work here is to prove termination. Let me quickly convince you that if it terminates, then we're done. Proof. So the proof is, as usual, by induction on the number of passes through this outer loop. There's a few things to check. The first is I'm going to check that at every stage G is actually contained in the ideal I. This is initially true because F is in I. You'll notice G and F are actually sequences, but I'm writing them as sets. So what I mean here is the underlying set of G and F are contained in I. But this won't confuse you, so let's just write it like this. This is initially true because of this, and if some remainder is added to G, well, by the inductive hypothesis, P and Q, which are in G prime, which is G from the previous step, those are in G, those are in I rather, right? Because they're in G, and G in the previous step was proved to be contained in I. That's the inductive hypothesis. So we have P and Q in I, and hence the S polynomial in I, because it's a linear combination of P and Q. But if you think about this division, well, that division there is going to write S PQ is equal to a sum of stuff, quotients, and then things that are in G, and then plus the remainder. But this is in I, and these are all in I by the inductive hypothesis. So then R must also be in I. Okay, so then that proves the inductive step. Clearly, the way it's constructed, F is a subset of G because we just keep adding things to the initial G, and the initial G is F. Now note that the algorithm only terminates when G is equal to G prime. And that means that we looked in the for loop through every pair of distinct elements. We computed the remainders, and we got 0. Which means that by Buchberger's criterion, G is a Grosvenor basis. What that means is that it only remains to prove termination. If we can prove this algorithm does in fact terminate, then it will return a Grosvenor basis for I with F contained in G. All right, but before I prove termination, are there any questions? Okay. To prove termination, let G1, G2, G3, and so on be the state of this variable G at the beginning of every iteration of the for loop. Okay, so that is, we have f is equal to G1, which is contained in G2, which is contained in G3, and so on. So in some steps of the inner for loop, nothing gets added to G, right? In that case, Gi will be equal to Gi plus 1. And then in some steps, something is added. And in those cases, Gi plus 1 will be equal to Gi union some remainder. Right? So in one of those steps, so in a step that looks like Gi contained in Gi plus 1, which is Gi union some remainder, then we have R equal to S PQ divided by G prime being the state of G at the beginning, even before the for loop, right? So in the beginning of that step of the outer while loop. Note that by the division algorithm, this remainder has a property that none of its terms are divisible by any leading term of an element of G prime. What that means is that if I look at the ideal generated by the leading terms of all the things in G prime, and I compare that to the leading terms of all the elements in Gi plus 1, well, G prime is one of these, right? It's the state of G at the very beginning of the first pass through that inner for loop, so it's one of them. So it's contained in Gi plus 1, so I have this containment here, and I claim that's a proper containment. Why? Well, because by definition the leading term of R is in here, but the leading term of R is not in here, because remember, for monomial ideals, if the leading term of R were in there, it would have to be divisible by the leading term of one of the G's in G prime. But that's not true. So that's a proper inclusion. Note that in fact we needed something a little bit weaker than what the division algorithm gives us, right? The division algorithm says no term of R is divisible by the leading term of G. But actually here we only needed the leading term of R not to be divisible by anything, the leading term of anything in G prime. And in fact, that's the basis for a kind of refinement of the Buchberger algorithm that Will and I worked on recently. So yeah, we're using something a little bit weaker than what the division algorithm gives us here. But the point is that, well, we have this proper inclusion, and we have a proper inclusion every time the algorithm adds anything to G. So if we look at this chain of ideals, by the ascending chain condition. That is, all ascending chains of ideals in a polynomial ring over a field eventually stabilize. That was the Hilbert basis theorem, essentially, right? Which we proved earlier. So by that theorem, this must eventually stabilize. If it eventually stabilizes, that means this can never happen. For that to never happen, it can never be that you ever add anything to G. But that means that past some stage in the algorithm, G is equal to G prime. Therefore, the algorithm terminates. And by what we said earlier, if it terminates, it's reached a Grosvenor basis. So we're done. So this algorithm, it's not the most efficient algorithm for producing a Grosvenor basis. There are variations on this idea. They all, as far as I'm aware, in general hinge on dividing S polynomials by the generating set. So they're sort of all oriented around S polynomials and have a similar flavor. But you can be more efficient than this, but this is existence. So we'll say more maybe next lecture about what we want Grosvenor bases for. Maybe I'll briefly, maybe I'll just say this out loud, since I mentioned reduced Grosvenor bases already. So a Grosvenor basis for an ideal is not unique. However, you can define a kind of minimal, the point being that there can be redundancy in a Grosvenor basis. Like if you take a Grosvenor basis and you throw in extra polynomials, well, you can do that in a way which still makes it a Grosvenor basis. So there's in some sense it's obvious that Grosvenor bases are not unique for that reason. But if you insist on a kind of something like linear independence, it's not exactly linear independence, but it's very similar. Maybe I'll just let me see if I can find some space here to put the relevant notion of linear independence. So to say linear independence for a Grosvenor basis, the definition is that for all P and G, no monomial of P is in the ideal generated by the leading term of G with P removed. That's a bit like linear independence, right? Which would say that in a linearly independent set, no vector can be written as a linear combination of the others. And this is kind of the same idea, right? So that's the relevant notion of linear independence for a Grosvenor basis. And you say a Grosvenor basis is reduced if the leading coefficient of every polynomial in it is 1, which is easy to arrange, right? Just divide through. And if it satisfies this sort of linear independence condition. And a reduced Grosvenor basis is unique, which is quite remarkable, right? It means that you can tell if two ideals are the same. That is, if you're just given two generating sets, you can tell if they generate the same ideal by computing for each a reduced Grosvenor basis, which computing a reduced Grosvenor basis is just an extra step after computing a Grosvenor basis in the way we've just done, so it's also algorithmic. So you can take your two generating sets, compute a reduced Grosvenor basis for each, and see if they're the same. And they are the same if and only if those two ideals are the same. So that's really quite remarkable. So that's the kind of the last thing I want to say about Grosvenor bases. So I'll hand over to you, Ken. Are there any questions for me before Ken gets started?
Yeah, I have some questions.
Yeah.
I was going to ask if there's some relationship between if the number of steps that the algorithm takes is related to the dimension maybe of the ideal or the variety. But then I saw this ascending chain condition, and I remembered you said something like the dimension is defined in terms of this. So it seems like a tautological statement maybe that the dimension is actually just how many steps this algorithm takes or related to that.
Well, the thing is, you could start with a really bad generating set, so you could make as many steps happen as you like, essentially by kind of just having more garbage in your initial input. So I don't think you can really look at just the number of steps. But if you're asking, I think what you're getting at is something like, is there some way in which you can recognize geometry in the behavior of this algorithm, whether it's the number of steps or something like it? I don't know. It's an interesting question.
I guess really I wanted to say that the worst case complexity of this algorithm is n squared times something. And what's that something?
Oh, the worst case complexity is very bad. See, if we go back to the algorithm for a minute.
Because each step is n choose 2 in the Grosvenor basis.
Yeah, that's right. But remember, in the next step, you have to look at all pairs in the new G.
Right. So n increases.
Yes, okay. That's right. So when you actually, I've watched computers do Grosvenor basis calculations for, I think the longest calculation I've ever run was a month, non-stop. So I was computing some not invariant and actually many calculations in various areas of mathematics reduced to Grosvenor basis calculations at the end of the day, so it's not that unusual. So what it looks like is you start with your initial generating set, which might be 10 polynomials, and seems pretty tame, and then you start computing a Grosvenor basis, and now it's 20, now it's 30, now it's 40, and then you can start reducing it back down, so then it goes back down to 15, and then it's 50, and then it's 60, and it's 100. So the process of the algorithm is the worst case complexity is very bad, and it's quite difficult actually to know ahead of time how bad is it going to be, and that in some sense probably has something to do with the complexity of the geometry, but I think people have thought about that, and computational algebraic geometry has things to say about that, but I don't know that much about it right now.
The other thing to note is that the dimension is it's not exactly the maximal chain of any old ideal, right? It's
exactly,
prime ideals, and you're not guaranteed to get prime ideals here, so they can go to as long as they want, right?
Yeah, that's right.
Okay.
Yeah.
It also seems like this is just this just sets the stage in a sense of here's how to brute force the Grosvenor basis. Now go ahead and cut out faster algorithms from this that do this step a little smarter.
Yeah, that's
depending on your situation.
Yeah.
Also, please tell me you didn't write that algorithm you're running in Python.
No. That was written.
I think I know why it was running for a month.
No, it was written in Singular, it's just a scripting language on top of their C++ implementation. So all the Grosvenor basis calculations are running in C++. I think they're.
Isn't everything just a scripting language on top of C++?
Yeah, kind of.
That's Roblox, that's Python, that's...
All right, shall we proceed to
So
the
then
next?
you had this month-long calculation you had it on the VM, right? Because otherwise, surely you would have died.
No, it was just running on a cluster of machines at UCLA.
Did you remember
Oh, wow.
to make it print like progress updates?
Yeah,
So
but
you
it's
know it
it's
wasn't like
it's a bit like watching a deep learning model train, though. You can drive yourself mad by watching Grosvenor basis calculations. It's like, yeah.
Awesome.
All right, I'll disconnect.
All right. Special move. What is special move?
Oh yeah, you can make the camera do something neat. Attach as listener and put yourself in orbcam, everybody, and then Kenneth, you can engage that.
Oh, so I can't see what's going on though.
You can click orbcam as the speaker.
I'm clicking on.
Oh, if you clicked it after you
Yeah,
activated.
but then I can't click.
Yeah, that's right. So you get this kind of.
Oh, so activate it. I click on all. Nothing happens. I guess I can't see this.
Yeah, it's not for you.
Can you guys
It's
see
for
what's
the
going
audience.
on? Oh,
Yeah,
it's not
it's
for me.
everyone.
You'll see the
all
recording.
Cool. All right, sounds good. Let's go over the board set number 2. Before I get started, are you planning on saying anything about reduced Grobner bases next week?
I don't think so. Maybe if it comes up somewhere, I'll say a bit more about it.
You said what they were. That's basically cool. Sounds good. So I think, yeah, so I'm going to take probably today and maybe not all of next week, maybe some of next week to finish off elimination and extension. And yeah, so most of this will be a bunch of examples. So it'll be a lot of calculations and maybe 1 or 2 drawings. So let's see how we go. So this is chapter 3 of CLO, so it's Elimination Theory. So I'm first going to say a few words about tying this to something you may have seen before. So remember when you guys learned linear algebra, you learned about Gaussian elimination as a method to solve systems of linear equations. And when we did Gaussian elimination, well, elimination is in the name. And so what you do is you try to eliminate variables by subtracting rows of a matrix from rows of a matrix from other rows, right? And eventually you end up with what you might call a reduced row echelon form, where a lot of variables have gone from subsequent equations, and then you do this back substitution, from the simplest equation back to the more complicated equations to get your solution. So what we're doing with elimination and extension here with nonlinear equations is going to be following a similar set of operations. We're going to try to eliminate variables, and then once we've eliminated variables, we'll have some simple equations, simple in the sense that they involve fewer variables, and then we solve those and back substitute. And we'll see actually when we try to do this in the nonlinear case that you can't always do this. So there'll be some theorems telling you when you can and when you cannot perform the back substitution steps. Okay, so I don't think I'm going to write this down. This is just a motivation from linear algebra. And so what I'll do is start with an example. And this is going to be kind of a long example, and it will illustrate what I kind of said in passing. Okay, so we'll start with an example. So we're going to start with just a bunch of equations. All right, 1x plus y squared plus z equals 1, x plus y, z squared equals 1. Okay, so if you have a set of equations like this, I'm going to call this set of equations maybe star. All right, I'll refer to it later. And of course, associated to sort of equations like this, you get an ideal, right? So you have an ideal associated to this variety cut up by these equations. And the ideal is just going to be basically the same stuff, right? Written in a slightly different way, but I'll write it down. Generators, I'll write like this. So hopefully by now we're kind of seeing this before. Okay, so yeah, so these are commas, right? So this ideal has 3 generators. Okay, so let's go to the next board. I guess I don't have to move. And I'm going to claim a Grobner basis for this ideal. I'm not going to compute it. You're welcome to check that this is indeed a Grobner basis using Buchberger's criterion, but I'll leave the computation of it as an exercise, right? As I think the book does as well. So Grobner basis for, did I call it I? I think I did. For I is, so I'm going to call it G1, G2, G3. So there are 4 of them. And I'm going to be careful writing this out because this is not as symmetric as the original generators. Okay, z squared minus 1. Second one is y squared minus y minus z squared plus z. Third one is 2y z squared plus z to the 4 minus z squared, and the fourth one, z to the 6 minus 4 z to the 4 plus z. There's a 4 here. 4 z cubed minus z squared. Okay, so this is a Grobner basis for I. So I'm just gonna pause here and stare at this and make a few observations. So the first one, G1, right, is just one of the original generators. So that's got variables x, y, and z in it. This G2 and G3, right, they only involve variables y and z, right? So this is something that's going to be relevant later on. So let me just make a note of it. Right, and so these two belong to the subalgebra generated by y and z. And the last one is even better. The last one here just has one variable. And so what I mentioned earlier about getting equations that involve fewer and fewer variables is playing out here, right? We found the Grobner basis in this particular example, or at least I claimed there is a Grobner basis in this example, such that the number of variables kind of that are involved get fewer and fewer as we go down the list. And finally, we get to G4, the fourth one, where there's only one variable. And when you have an equation involving one variable, at least in principle, we think that we can solve it. At least with a computer, we can try to find the solutions, right? And so, of course, when I'm talking about solutions, the reason why I'm doing this, I'm trying to find the points in this variety, right? And what this means is solving the equations G1 equals 0, G2 equals 0, G3 equals 0, and G4 equals 0 simultaneously. And the solutions of these equations is the same as the solutions of the equations presented in the previous board. So this, so let's do it, right? And this is actually somewhat involved. I'll give some of the details, maybe not all of it. So note that this
Hello? Patrick has a question in the chat.
Yeah.
Yeah.
So you kind of made a passing comment about this Grosvenor basis not being as symmetric as the original set of polynomials, which is symmetric. Would like a reduced Grosvenor basis have been symmetric, or maybe are there other choices of Grosvenor bases that are like this set but with the variables rotated around or something.
I think this is a reduced
Probably
Grosvenor
not,
basis.
Dan.
Let's see. I think this. I mean, I think
Yeah, there you go.
if you get rid of the 2 in
So that's
G3,
it. No.
so if you divide through by a half,
Yeah.
I think.
Yep.
Let's see. Leading terms are x, y squared, yz squared, and z to the 6. Yeah, this is a reduced Grosvenor basis.
Oh, okay.
Cool. So yeah. So thanks, Dan. This is reduced. And actually, I forgot to say this is Lex order.
You telling me you computed all those
Yeah. So I guess
S polynomials and you
Yep.
Sorry.
No, I didn't claim that.
Yeah.
I didn't claim that I checked it was a Grosvenor basis. I claimed that I checked it was reduced. So I just have to check that no monomial in say G4
right.
is divisible by a leading term of the other ones. You might believe I can do that.
Okay. Yes, it sounds plausible.
Yeah. So there's no reason to believe that the reduced Grosvenor basis should be somehow in some nice form. It's not even clear what nice means, right? It just so happens that the original set of equations looks nice to us.
Yeah, I think this is actually
Okay, so let's take a look at this G.
Sorry, Ken, I'll just make one more point here.
Yeah, that's all right.
Yeah, I think this is actually kind of a deep question. So a reduced Grosvenor basis is the most explicit expression of an ideal. Explicit in the technical sense that if you have 2 explicit presentations of 2 ideals in that way, then you can tell if they're equal or not by just looking at the coefficients, right? So it's like the normal form of an ideal. But that doesn't mean that it's the most intelligible form of presentation of the ideal. So in this case, the original equations exhibit some symmetry, which we could talk about, which is actually interesting and is an important feature of that variety, but it's much more obscure in the reduced Grosvenor basis. And that's universally true. So it's not that you don't lose something by only having the reduced Grosvenor basis. Depending on how you present these things, there's some advantage to the implicit form, which is kind of maybe exhibits the symmetry but isn't a reduced Grosvenor basis, versus the reduced Grosvenor basis, which has other advantages, and the differences between those two are quite interesting. So, yeah, this is a good question.
Is
maybe
the reduced
right order to do.
Oh, sorry. Yeah, I was just going to ask if the reduced Grosvenor basis is unique, but you still have that's still with respect to a particular monomial order, right?
Correct.
So if you choose a different monomial
correct,
order, yeah, okay.
Yeah, but we'll see that the reason why we're using Lex order here is that for elimination theory, this is actually the right one to use. But maybe not for presenting this particular variety. Maybe the Lex order is not what's making these Grosvenor bases look kind of, to us it looks like kind of strange, right? What is this variety? So, okay, any other questions? Comments? Okay. All right, so let's look at G4, and this example has been cooked up in such a way that we can actually factorize this degree 6 polynomial. Usually, you don't have much of a chance in doing such a factorization. I'm going to try and make my 2's and z's look distinct. There you go. So you factorize it, and here you can solve this, right? So solutions to G4 equals 0 are, there are a bunch of them. They're going to be z equals 0, 1, and whatever the roots of this quadratic thing is, right? That. And once you have, oh yeah, K better be C. So we're gonna, I forgot to say this. We're working over complex numbers because we're solving equations, right? For elimination theory, where our goal is to find points. We don't want to deal with finding rational points over funny fields. So we're just going to work over complex numbers. I'm going to just say that at the beginning. Work over C for this section, for this lecture. Yeah, and you'll see that actually some of the theorems that I'll present later on require the base field to be complex numbers for the conclusions to hold. So yes, so k equals C. So maybe I should just change it on this page as well. So these k's should all be C's, just so that we know we can solve things, polynomials. All right, there we go. All right, so we've got 4 solutions. 2 of them repeated, but so now we can take let's take 0 and 1 and let's work backwards and see what we find. These are probably not too hard to do, right? Now you look at z equals 0, so let's look at that one. You substitute in the second to G3 equals 0. How should I write this? Maybe I can fit it on this board, right? So I'm gonna draw a line down here, and okay. So if we want to do z equals 0 and G, okay, when z is equal to 0, G3 forces G3 to be 0, so we can't do much there. So we're going to go to G2, right? I'm just going to say this implies G3 equals 0, right? And so you don't need to deal with that. Z equals 0 and G2 equals 0. This gives us an equation which is 0 equals y squared minus y, right? So this implies y equals 0 or 1, right? And once you have y equals 0 or 1, you can figure out what x is from G1, right? So now, this is going to be, you guys can figure this out. So I'm going to just kind of skip that last calculation, right? ... So you get, right, solutions, which is, so I wrote this down. This is going to be 1, 0, 0. And 0, 1, 0. Right, solutions. So these are solutions to all of the equations. And right, yeah, so z is 0, y is either 0 or 1. For each of these, we'll work out x. Well, x is either 1 or 0 for those cases. And right, so we've got 2 solutions. Let's work out the rest. So there's one more. There's one more here. When when z is 1, then so when z is equal to 1, right? So I'm not going to be able to fit it down here. I'll just write down what the solution is. When z is 1, now G3 equals 0 has a consequence, which is y equals 0. And once you work that out, when y is 0 and z is 1, well, x has to be 0, right? So we get, okay, so these are kind of just back substitution, like really just working what the equations are. So this is 0, 0, 1, right? So we found 3 solutions. There are 2 more, and I'll do that on the next board. So the last one here, I guess, so now if z is equal to minus 1 plus or minus root 2, oh yes, thank you. Okay, so now if z satisfies, if it's equal to this, then i.e. z squared plus 2z minus 1 equals 0, then we can actually use this. We don't have to use the root form of like minus 1 plus or minus root 2. We can actually use the equation z squared plus 2z minus 1 to simplify the equations that come earlier. And you actually find that in this case, G2 doesn't do anything. And G3 leads to, what did I write down here? Maybe this is probably not, yeah, so I actually did work this out. I don't know if this is worth going into here, but I'll tell you what the punchline is. Basically, you get Z equals Y equals X in this case. So there's some calculations. How about this? Who wants to see the calculations? It's essentially just kind of high school algebra. If you give me permission to skip it, I will skip it. Okay, sounds good. So yeah, so basically, you know, I wanted to write this out in some detail because this illustrates what we actually do, right? I'll just kind of recap a little bit. We solved G4 equals 0. We found, you know, in this case, it was an equation involving only one variable. Found some like actual solutions that are numbers, right? And we just substitute them back. And in this case, we were able to do this. Each time we just substituted them back. There wasn't any obstruction to us doing this back substitution, but sometimes there is, right? We'll see an example later on where, you know, you can't just substitute solutions that you get from early equations back up without worrying about whether things will have solutions. You actually see situations where, some things don't work out. So this is an example where everything works nicely. Okay, so the other thing that we saw was in this case, the equations or the Grosvenor basis that we got fewer and fewer variables as we went. So we're gonna make a definition here. So we're gonna define the elimination ideal. Okay, so I'm going to write down some notation. So I'm going to let R0 equals R, and that's going to be, I guess, equal to, maybe this is not the best way. I'm going to let R0 equals the polynomial ring. And then I'm going to have R1 be x2, xn, right? And then I'm going to have R, I guess I'll have Ri, k xi plus 1 to xn. So you can see why I'm doing all these Ri's and so forth, because it gets a little bit K, right? And I guess the inclusions go the other way. So I'm going to define the subalgebras of R. So this R0 is actually R here. And I kind of wrote this reverse. I usually write it the other way, but that's okay. So, and I'm going to define these ideals, right? I'm going to intersect I with each of these Ri's, right? So I'm going to define, and define I, okay, L equals I intersect R, L. And I guess, you know, I be an ideal of R, right? You have this sequence of subalgebras, and then you define IL to be the intersection of I with the Lth piece of this. And we're going to call this the ith elimination ideal, or Lth elimination ideal. Okay, so we define it like this, and basically the reason why we do this is because, you know, we claim, or at least in the previous example we saw that the Grosvenor basis that we had naturally fell into you know, this sequence, right? The variables kind of dropped off one by one, and so we make a general definition like this. And the claim here is that I guess the punchline later on will be, yeah, the Grobner basis does this in general, right? It actually does respect each of these pieces that we've defined here, and this IL can actually be worked out using the Grobner basis with respect to the Lex order. Okay, so that's definition. So note that IL is an ideal of RL, right? But not necessarily for the other RJs. Not an ideal of Rj for J less than L. So why is that? Well, you know, when you increase that, when you decrease that J, you're letting more variables in, and when you multiply IL with variables that it hasn't seen before, that's not in the ideal. That's going to make it go outside of the ideal, because IL is actually a subset of RL, right? So it's almost never an ideal of Rj unless it's like 0, right? So yeah, this is a point to keep in mind. It's called the elimination ideal, but it's really just an ideal of that level, or of that L, if you like. Okay, so the elimination step, right? When we eliminate variables, it's really the same as finding elements of IL, right? Because you can also think of this sequence of RJs that I've written here as eliminating variables as you go to the right, right? Each time you go a step to the right, one of the variables disappear until you get to the end, all the way to the right, all the variables are gone, right? So finding elements or finding generators of IL is really the same as eliminating variables, because we're kind of eliminating variables from the ideals. And the theorem, the elimination theorem here, says that in fact our example generalizes, right? We actually have already done this. The Grobner basis allows us to fulfill this goal of eliminating variables and finding generators for IL. So theorem, this is called the elimination theorem. Okay, so let I be an ideal of R and G be a Grobner basis of I with respect to the Lex order. And I'm going to underline this. You need that. Can't use any old order here. And I guess I should say, you know, I don't think it matters which one order, but let's fix one just so that we are explicit. Then for all L equals 0, 1 to n, the set GL, so he's just intersecting the Grobner basis, which is a set of finitely many things, and we're just going to do that. This is a Grobner basis for IL. IL. And this is IL as an ideal of RL. Okay, let's stare at this for a little bit, right? So what this means is that
With respect to
the
the
situation
Lex
where
order as well.
yes. Oh, yeah.
It's kind of been implicit, but since we've switched rings here, it may be a little confusing if one doesn't say that,
Yeah. Yes. Thanks, Dan. Yep. So yeah, we have to be careful here. The Lex order is the one we're using for the original ring and all of the RLs. And what this says, right, when we go back to our example, is that the situation where we compute a Grobner basis with Lex order, the situation where the Grobner basis naturally falls into a situation where the variables get fewer and fewer is generally true, right? So, and in fact, not only that, these subsets, right, when we just look at the Grobner basis consisting of those fewer variables, actually is a Grobner basis for IL, which is the elimination ideal. And that's important because we're going to use these elimination ideals to solve the original set of equations, right? So finding generators for them, describing the ideal, finding the points is important. Okay, so let's move over to the right to prove this. Okay, so proof. Is everyone back? I only see, oh, the rocks are obscuring. Oh, you guys are
They're up in the trees.
hiding behind rocks. All right. In the trees. Awesome.
You might need to walk this way a bit, Ken.
Okay,
The orb,
so let's do the proof of this. The
the
proof
orb's
is
kind
that.
of gone over a bit. I don't know why.
Oh, sorry.
Yeah, just walk over this way. But yeah, that's better. Yeah.
Oh, left. Here?
Yep, all good.
Cool. There we go. Let's check. Oh, thanks. Okay, so the proof is quite neat. You know, one of these proofs that you do and you're like, wow, that actually was very short and did exactly what we needed it to do. So we need to show it. So what do we need to show? We need to show that the GL, right, is actually a Grobner basis. And so the way we do it is, so we look at the ideal of leading terms, and we're going to make sure that it's TIL. Right, so compare these two. So one direction is clear. This is clear. Right, so since GL is a subset of IL, right? Okay, so conversely, suppose suppose F, right, you want to take an element of IL, right, which, let's remind us, this is actually a subset of I, right? We want the leading term of F to be divisible by LG, a leading term of G, for some G in GL, right? To be divisible by LTG for some G in GL. Okay, so, right, because if you've got monomial ideals to check, right, whether one's in the other, you just have to check divisibility, right? So that's what we're doing. And we're going to use the fact that G is a Grobner basis, so we can always find some G to do this. We don't know whether it's in GL, but we can always find some G in G to do this, right? So we'll use that fact, right? Since G is a Grobner basis, right, of I. Be careful here because there's multiple different ideals floating around. So we can find G. So just some element of G such that LT G divides LTF, TF. Okay, so that's fine. So now we have to make some argument for why G is actually in GL, right? And then we're good. And so here's where we use the Lex ordering. So note that LT of F is actually in IL. So LT of G is in RL. Okay, so why is that, right? So what does being in IL and being in RL mean, right? It just means that the leading term of F and leading and consequently the leading term of G don't have any variables from x1 to xl, right? So RL means only variables that are in there, L plus 1 and to n, right? So it does not have variables x1 to xl. And so if LT of G divides LT of F, right, and LT of F, only has variables from L plus 1 onwards, well, of course, the LT of G also has that property. Right, so now we use Lex order. So now we use Lex order. How do we use Lex order? Well, we know that LT of G is in RL. I'm going to say this and then write it down. So it's lexicographical order. We know the leading term only has variables xl plus 1 onwards. So any subsequent terms can't have anything from x1 to xl, because if that's the case, it wouldn't, well, the leading term wouldn't be the leading term anymore, right? By Lex order, even if you have one variable that precedes it, well, that's going to be the leading term. So, so because we're using Lex order, maybe I should say since by Lex order, non-leading terms of G are also in RL. So I'll just put in brackets here. Cannot have variables x1 to xl, right? They just can't. And so another way of saying it, that terms cannot have variables x1 to xl is that is in RL, right? So this means therefore, right, if each term of G, if they're all in RL, well, G is also in RL, so we're done. So that's what we wanted, right? We wanted to show that there exists some G in GL, right, such that this is the case. Well, G is in G and is in RL, and so since GL is an intersection of these two, well, G is in GL. Okay, so this does it, right? And so this tells us that the Grosvenor basis found by Lex ordering is actually adapted to that sequence that we wrote down earlier, the R0, R1, R2, and so on. And moreover, when you take the subset of the Grosvenor basis associated to each of the RLs, actually generates the ideal IL. And it's a Grosvenor basis of IL. Okay, any questions?
Kind of seems too easy to call the theorem almost at this point.
Sorry?
It kind of seems too easy to call a theorem once we've set everything up this way. I guess historically, this whole subjective elimination was much more complicated, but approached this way, it just kind of falls over.
Yeah. How did people do this without Grosvenor basis?
Well, I mean, add resultants and stuff like that, which are
right,
later on in the book.
It's way... Yeah. So I guess resultants we won't talk about, but it is used in the proof of the extension theorem, which I'll probably get to next week at this point.
Right.
And yeah, I don't know. Maybe I'm not sure whether since I have more time, maybe I will put the proof in. But I don't know how complicated resultants are to kind of just introduce and use, right? But we'll see. We'll see. So probably have time to do one more example today, and then I'll finish off extension next week.
Is there
So yeah, so the theorem,
there-
the extension theorem. Sorry, yeah?
is there any
Got a question?
like this theorem? Yeah, can you hear me? Hello?
Yep. Yes.
So this theorem is specifically about the Lex order. Is there any statement you can make about like a situation where you don't have them, like are just with a different monomial order, or is it hard to state something?
Well, I guess the goal here is to do elimination theory, and I guess what the theorem is saying is that if you want to do elimination theory and you want to get bases for these elimination ideals, Lex order is one you can use to give you what you want. If you use a
Right.
different monomial order, this theorem does not work, right? I mean, it'll give you some other Grosvenor bases that will have other properties, but are you saying maybe we can put a different filtration on R and do it that way? I don't know.
Yeah, I was wondering, like, I don't know, with a different monomial order, maybe instead of the R0 up to Rn, there was like a different chain of sub algebras that would relate to that monomial order. But I don't know, kind of an abstract
I mean,
question.
the monomial orders aren't just right. They're quite different, right? I don't. My gut feeling is probably no, that this is special to Lex ordering. Dan, what do you think?
Yeah, I think so. I mean, when you do this elimination theory in a way that's tailored to projective space, maybe there's a role for kind of caring about the degree, so something like graded Lex. But I think fundamentally you're not. I think
Right.
this is unlikely to say much interesting outside something that's Lex or graded Lex or Lex in some form. Yeah. But I could be wrong. I'm not really an expert in this.
Cool. Any other questions? Right. So, yeah. So let me say a few words and then finish off with an example, and then I'll leave extension theorem for next week. So, what are we trying to do in this chapter or in elimination theory? We're trying to solve equations, right? In algebraic geometry, we always say we want to solve systems of polynomial equations, right? And it's funny, like this is really how you do it. And it's not always the case that we end up doing stuff like this in algebraic geometry, but we are trying to solve equations, or at least study the solution of systems of polynomial equations. And so this is the same as finding points in the corresponding ideal, right? So solving equations f1 equals fs equals 0. But this is the same as finding points of vi, where I is the ideal generated by f1, right? We know this. So with the approach of elimination theory, right, we're kind of finding partial solutions. And this is kind of finding points in this VIL. So what's the point, right? Can we actually construct solutions of VI from these partial solutions? Well, in our first example, we were able to, right? The partial solution that we got as G4 equals 0 were just a bunch of numbers, 0, 1, 1, plus minus 1, plus or minus root 2. And then we found more and more components of this partial solution by going up the chain. And so that process of going from a partial solution and adding more and more components to it is what is called extension, right? And I kind of alluded to this before. In the first example, we were able to do this without any obstructions, right? It just works. We just substitute the numbers in like a high school student, and everything just came out. We just solved for all the numbers, and everything just worked, right? But this doesn't always work out. And the extension theorem here tells us when we can actually do this. Now, I actually thought I was going to do another example, but I think the other example is an extension example. So let me do it, and then I'll get to the more general kind of picture next time. So the example here is, the variety is going to be a very simple one. xy equals 1 and xz equals 1, right? And of course, this is the same as, looking at the ideal generated by xy minus 1 and xz minus 1, right? And of course, by now, right, when we see an ideal with generators, our first instinct should be like, let's find a Grosvenor basis for this. And so actually a Grosvenor basis, so I'll let you guys check this one yourself. This one actually is doable. You can actually just do it. But I'll just write down what the Grosvenor basis is. So a Grosvenor basis is xy minus 1. I'm going to call it g1, g2, just because that's what we've been doing. So g1 equals xy minus 1, and g2 equals y minus z. Okay. So in this case, right, we don't end up going all the way to equation with a single variable. So that doesn't always happen, right? Just because not all varieties are points, right? Varieties can have positive dimension. So sometimes you get to the end of your list of Grosvenor bases, and you find that there are multiple, there are still multiple, more than one variable, in this case, y and z. Right? No x though, x is gone, right? And right, so if we start solving from G2 onwards, right, if we solve, right, follow the same kind of strategy that we did before, solve G2 equals 0, what we get, well, we get a line.
Okay.
And sorry, you got a plane, not a line, because we're in 3 space, right?
Let's move
Yep.
over.
Yep. Sorry. I keep a count of 2 in my head. Every time I do 2 boards, I gotta move. Thanks, Dan. Cool. So, so we want to solve this, and you get y equals z. And so this is a plane in, I guess, C3. We want to see C3 or R3. I guess it doesn't matter in this case. I'm going to stick with complex numbers because I said we're going to stick with complex numbers. And I also said I wouldn't use C3. All right, you get a plane there. And the first elimination ideal, right, I1, well, if I've done this backwards, yeah, I've done this backwards, but that's okay. The I1 is I intersect K, Y, Z, right? And the elimination theorem implies that I1 is actually generated by Y minus Z, right? And that's, of course, a Grosvenor basis. Okay, so what have we done? We've solved this equation, and we want to go back and take this equation, take the solution y equals z, substitute it back into the first equation to get some get a set of full solutions to the original set of equations, right? See, we've only solved for we've parameterized, we've found a family of solutions in 2 variables only, right? So so like this thing here, right, can be parameterized by TT, right, because y and z are the same. T is just a parameter. I guess this is in A2, and I guess y is z, right? Yeah, so this gives us a plane, right? That's cutting through x equals 0. So and t is just any old complex number. I actually think the book uses real numbers, but maybe it doesn't matter. I'm going to stick with complex numbers. If it breaks, I'll switch it. Right. So which ones of these solutions can be extended to full solutions of the original set of equations? Well, let's remind us G1, right? So which partial solutions? So the partial solutions are these guys extend to full solutions. All right, so you look at G1. G1 was x, y minus 1, right? So you can see that if t is not 0, this always is okay, right? When t is not 0, you can just substitute x equals t, y equals... All right, x equals t, right? And y can just be 1 over t, right? And no other way around. Y is t and x is 1 over t, right? So if t is not 0, then x equals 1 over t works. X equals 1 over t solves G1 equals 0, right? So we get 1 over t in a, I guess, x, y, z, 3, right, as a solution to, to the original set of equations. So I'm just going to say as a point in VI. I is the original ideal. When t is equal to 0, you can't, right? Because when x is 0, when y is 0, there's no way you can put any value of x to make 0 equals to 1, right? So you can't. So we can see that two things, right? One is that it's not the case that you can always extend partial solutions to full solutions. And it looks like, at least in this very simple example, that most of the time you can, right? So in this case, as long as t is not 0, you're good. When t is 0, so for some special points, you get stuck. You cannot extend these to full solutions. And so we're going to see next week what is that criterion, right? And it will turn out to be the case that most of the solutions do extend, and we have a, I'll say a Zariski closed subset of the solutions which cannot extend. Last comment here that we've stated, we've only kind of done this in one variable, and the theorem that I'll state next week is really going to be just extending one variable at a time. It turns out that's fine because we can do this iteratively, and I'll say more about what this means next time as well. So I think I'll stop there.